I head up marketing here at SaltStack. I am happy to share this content with you today. I'm joined by C.R. Oldham at SaltStack. He's one of our senior software engineers and one of the main engineers who has worked on our proxy minion technology, which we'll talk about in more detail about today. And then also very happy to have both Edward Arcuri and Nathan Embry on the line with us today. And so in terms of how we'll run this webinar today, we'll give you a quick overview of some of the core technologies, core SALT technologies that were involved in this the Juniper event-driven infrastructure technology. And both CR and I will talk through that. And then we'll hand over to Edward and Nathan, and they'll dive into a demo and an overview of what they've created and what we're calling JEDI, or the Juniper event-driven infrastructure. So I assume many of you are familiar with SALT, but just a quick, history lesson here. SALT was started as an open source project about 4 to 5 years ago as a response to other configuration management technologies in the market. Thomas Hatch would use some of these tools, but for the work he was doing and for the infrastructures that he was managing, which were extremely large and extremely complex, he felt that it didn't quite do the job that he needed, and so he created SALT. SALT was initially created as a remote execution platform. Configuration management was built on top of that remote execution capability after the fact. And so, from that perspective, SALT is well known as a very high-speed and scalable, and very capable systems management tool that, of course, does configuration management very well. In that 4 to 5 years, the SALT open source project has exploded in popularity. We've got we pride ourselves on having a very healthy and vibrant and open and friendly open source community, and we chalk that up to the fact that that you can do a lot of cool things with SALT, and of course we're here on this webinar today talking about some of those things. We've seen companies, of course, like Juniper Networks, just a company like Google and Nutanix and Cloudflare use the SALT technologies to power some of their systems and infrastructure offerings. And we, of course, SaltStack, the company, and exists to maintain and encourage the SALT open source project. And of course, we have created other systems management tools and products on top of the SALT project as well. SALT's received a lot of recognition over the years in terms of its capabilities and both in terms of the open source project as well as the technology itself. We don't need to talk about those in detail. And then, of course, SaltStack, the company, provides, we maintain the open source project, we provide services and support, and we also have a commercial product called SaltStack Enterprise. The big difference between SaltStack Enterprise and SALT open source is mainly a graphical user interface as well as an enterprise API that allows for the more fluid and easy consumption of the massive amounts of data that are created with any salted infrastructure. And so I'll turn over the time and the mic to CR to kind of dive into the technology and the proxy minion technology specifically. We have a few slides here, and then we'll turn it over to Nathan and Edward at Juniper to go into more detail about the JEDI technology and work that they've done there. So, CR?
Good morning, everybody. SALT's fundamentally a client-server type of system. In this slide, you can see we have a master, which controls all of the minions. And in the middle between the master and the minions is the event bus. The event bus can use one of several protocols. Our default is 0MQ. We also have a protocol based on Tornado, which at the base layer is really just SSL. And also you can access minions through Salt SSH if you want to use a masterless type of setup where you prefer not to have a master in the mix. But we recommend the use of a master because it affords quite a bit more power. Also, on the left side of the slide, you can see the little blue icon that says reactor. That reactor icon represents one of the most powerful parts of Salt. The reactor can sit and listen to the event bus and respond to any event that comes across the bus to perform any kind of action that Salt might do normally. So, for example, if you're trying to keep some configuration files in sync and you want to make sure that they never change, you can configure a reactor to go out and watch for events that have to do with those files. And then if those files are altered, the reactor can fire off an event that will bring those files back into compliance. So also at the bottom of this line, you can see that we do have several different types of, we ported the Minion to several different operating systems. The Minion does run on Windows. We support all of the major Linux distributions. We also support AIX through our enterprise end of things, and we're going to talk about how we support other types of minions that don't fall into the typical category. That's what Salt proxy minions are for. In particular, the Juniper hardware that we're going to discuss today. So this is an example of remote execution. When you start up the minion requests a connection to the master, and this is different than some of the other configuration products that are on the market. Usually the master has to reach out to all the different devices that are being controlled, but Salt works the opposite way, where the minion actually initiates the connection to the master, which means you don't need to open any inbound ports on your minions unless you're using SSH, obviously. But in general, and by default, we open a connection from the minion to the master using 0MQ or over our Tornado transport. The master accepts that communication, and from then on, we have a persistent asynchronous connection from the minion to the master. We'll talk really quick about encryption there. Every minion generates a unique key that must be accepted on the master before the master will control the minion. And that key ensures that all the traffic between the master and the minion gets encrypted so that other devices that are on the bus can't eavesdrop on it. Salt supports configuration management, as Rhett mentioned before. We originally started out, Salt was just a remote execution engine, and we layered configuration management on top of that, because the remote execution part was so powerful. So most of the configuration files that you will create inside of Salt are just simple YAML. Everything is text in Salt. We wanted to keep it simple, so it's very easy to get started. To write states that actually perform actions inside your Salt infrastructure is very simple. You just write a few lines of YAML. Our documentation online is quite extensive between all the modules that we support, and you can look that up at docs.saltstack.com. So I mentioned earlier about the reactor, which is, I think, the most powerful part of Salt, which enables what we like to call event-driven automation. That means that the reactor, in conjunction with the master, simply watches the event bus, and any type of event that crosses the bus can be trapped, and actions can be taken based on that event and associated data with it. So that includes things like authentication events, when a minion starts up, maybe as soon as the minion becomes available, you want the master to do some things with it. Cloud events, if you spin up machines in the cloud, and when those machines become ready, then the event bus will see an event based on exactly what happened when the machine was spun up. File system changes I mentioned earlier, network and disk usage, all sorts of things are available through the event bus, and the reactor makes it possible to drive your automation based on that. So I'm going to diverge a little bit and talk about proxy minions. So we've discussed minions earlier in this call. Minions are the devices that are being controlled by Salt. And we wanted the ability to control devices that maybe did not have the ability to run a minion, either because they didn't have enough CPU or memory on board, or maybe there was a security issue and you didn't want to actually run an agent on the minion. So we developed this technology that we call proxy minions. The proxy minions look to the Salt master just like every other minion, and they can receive commands just like every other minion, but instead of controlling the device that they run on, they control some external device. And that's what this diagram shows. We have a Salt master and actually 3 minion controllers here. Each one of those minion controllers actually runs a regular minion, but then runs several Salt proxy processes underneath to control various devices. And I called those dumb devices in this particular slide. Apologies to our colleagues at Juniper. I don't really think your devices are dumb. It was just a placeholder for us to use. So you're able to control those devices just like any other minion, which means that you have the ability to drive your entire infrastructure from the network all the way through all of your servers with one product, and that product would be Salt. Just as a matter of explanation, if you're going to automate with a Salt proxy minion, you need one process per controlled device. That's not really as big a deal as it might sound. Our benchmarking shows that that's about 40 megabytes of RAM per proxy process. So on a 4 gig machine, you could run 100 proxies, maybe a few more. Proxies are configured through Salt pillar mechanism. Pillar is a way to distribute data securely from the master to appropriate minions. And just as an example, if you happen to drop into Salt's GitHub repository, we do have support for a couple of just sample minions. You can set this up so that you would have 2 control devices, one a regular minion, a second one maybe a REST API endpoint emulating a server, or maybe an SSH endpoint emulating a server. And in the examples that you'll find in the Salt repository, these servers have limited functionality. They can install and remove packages, stop services, and report some basic information. But that's just a way, if you want to play with proxy minions and see how they work, you can drop it into the Salt repository on GitHub and take a look around. If you want to create your own proxy minions, you need to write a proxy module in Python. And it really only needs 4 functions to do anything valuable at all. A ping function, a virtual function, which is something that we use in Salt to know when it's appropriate to load a module, an init function that sets up everything that you need to do to talk to your controlled device, and then a shutdown function so that when the minion shuts itself down, you can clean up those connections, for example, maybe SSH connections or other network connections to your device. And optionally, you can configure functions to return grains information. Grains are information that gets sent from the minion to the master about each individual minion, so things like RAM and disk space and stuff like that. Also, proxy minions are totally supported inside the reactor and the beacon system, so you can even react on events generated by your devices that get picked up by the proxy minion, and those events get set on the bus, and then you can go from there. Some proxy minion modules that we already have in place. We have one for Junos, we have Kronos, we have a proxy minion for ESXi, for Dell FX2 chassis, for Marathon, which is the container management system, Napalm, which is it's kind of a generic network automation framework. Also NXOS for Cisco, even Philips Hue light bulbs, we have a proxy minion for those. And then I already mentioned the samples, the REST sample and the SSH sample are available in the repository.
All right, thanks, CR. And so, yeah, of course, we're going to be focusing the rest of our time today on the proxy minion that the Juniper team has created for Junos and is powering this Juniper event-driven infrastructure. Before we turn over the time to Juniper, though, I just want to share a couple of examples of how our customers are using a Salt proxy minion within their salted infrastructure. Adobe, for example, among many other things that they use SaltStack for, they have had a very manual process in the past of provisioning blades as well as the racks that the blade servers run in. And so specifically, the Salt Proxy Minion is used to provision those blade server racks at scale. And we're talking thousands of these racks and devices that Salt is used to help both provision and maintain. And then many of you may have seen, CR just referenced the Philips Hue light bulbs. Our friends over at SUVA developed this integration to show off kind of the power of Salt, kind of the real-time nature of Salt in a demo that they created. And these videos of this demo is available on our YouTube channel and online. But you can see how Salt is used to both turn on and turn off those light bulbs you can see at the bottom of the stage there, and turn them to different colors and so forth. So a pretty slick, maybe not necessarily real world example, but it's a good representation of the type of power that is available via the SaltStack automation platform and through the Proxy Minion to devices and systems that may not be traditional to a data center and the traditional servers that are managed with Salt. And so with that, I'm going to turn over presenter rights to Edward Arcuri with Juniper. Just make sure I can find him in the list. Edward, I've handed that over to you. Hopefully you see that.
Hey, Red, it says that I'm still waiting. There we go.
There we go. Yeah, sorry about that. We're having GoToMeeting issues today, obviously. Okay, so there we go. I see your slides now. I'll go on mute and turn it over to you, Edward. Thanks.
Thanks. My name is Edward Arcuri. I'm the director of the automation and programmability team in our Global Center of Excellence at Juniper. I also have with me one of my colleagues, Nathan Embry, and we're going to do a quick presentation on Juniper automation capabilities, how we get here, the types of things that we think about as automation engineers, and why we chose SaltStack. And then Nathan will go ahead and do a demo for us as well. And I think the demo is between like 15 and 20 minutes, so you won't have to listen to me very long. So, for those that don't know, this is our CEO, Rami Rahim, and a few years ago, he essentially put a stake in the ground and said that the transformation in the networking world is going to come down to automation. And for those of us that have been doing automation for a very long time, we were happy to hear this, and we were also terrified at the same time because of the amount of work that has to go into it. And luckily, because Junos is such a good operating system, it was originally designed with automation in mind, or programmability. So the Junos automation stack, when you get a Junos device, you are always going to get this stack. All these capabilities are built into Junos. And from day one, something I wanted to point out was the CLI rests on top of an API that we have had since the beginning. And when Junos was originally created, it didn't have a CLI. It was always API driven. And the reason for that was because the people that created Junos knew that it was going to have to go into a distributed system or a network. And you don't manage distributed systems through CLIs normally. What you do is you manage them programmatically through an overarching software architecture. So the most requested enhancement for Junos when it first came out was to put a CLI on it so that network engineers could actually log into the device and do something with it. So you'll notice on the right-hand side that CLI actually sits on top of that API. And the CLI really is only about 200 lines of code. All the the guts of how Junos works actually resides in something called MGD, or management daemon, and both the green layer and that red layer there, that's everything that MGD brings for us. So we can build on top of that, because we use standard protocols and interfaces to be able to build technologies on top of it, things like our PyAZ framework, which in turn we use to build our SaltStack modules. So as I said, Rami put that stake in the ground, and we knew that network automation was going to be a journey. It's not just something that you turn on. There are no easy buttons, really. So what started out was, most customers of ours took that as, great, we need to write some scripts, do some runbook technology to make provisioning easier, maybe gather some information from the network. And that's what we call human-driven automation. And I'll talk about control systems here in just a minute, just some basic things. But that's mostly what happens is, something happens in a network and we react to it, or we have a plan to do something in the network, and we automate that by having a human being kick off a script or some sort of run book. And then once it goes through that, they get the information back and they look at it and they determine what happens next. So what we're trying to get to is the evolution of that, which is event-driven automation. And I've talked to many other automation engineers who are not in networking, that actually come from the oil and gas industry or the aviation industry or manufacturing. And this is how they run things today, is usually through some sort of event-driven automation. There's very little human interaction with the systems themselves, because they know that to really see the benefits of automation, they need to let it do its thing. And they can take the knowledge from the subject matter experts for whatever industry they're in, and they can codify that and put it into something that uses this event-driven automation to take away a lot of the basic things that we know what to do as humans, and we have to keep repeatedly doing that. So not only are we pushing information into the system, but we're also pulling it back out. That's, in our case, would be telemetry. And then we do something based on rules with that telemetry. So the next thing, and this is something that Nathan and I and other members of our team are working on, is actually getting to the artificial intelligence, in air quotes, and machine learning, to actually not only have the subject matter experts codify their knowledge and put that into the event-driven system, but also to use algorithms to pull back enormous amounts of data from our systems and infer what needs to happen next. Okay? So this is very far off in the future. Might be a little bit closer than some people want it to be, but we are working on this today. And to get to the model of what Juniper has put forth as the networking grand challenge, called the self-driving network, we have to use an event-driven infrastructure and this machine-driven automation to get to that. So these are the types of things that we as automation engineers think of. We'll talk about the automation continuum, basic control systems theory, and then event-driven automation. So for all automation engineers, regardless of industry, use levels and stages to essentially think about how do we move things forward. As you can see, the levels, there's different levels that we can do. If you're level 1, there's no assistance provided in an automated fashion, right? But if you go, as you go up in the levels, if you get all the way to a 10, this is where a computer decides everything, and it doesn't even let you know why it decided it or what's happening. This is an autonomous car, right, like Google has. This is where we want to get to with self-driving networks as well. And there are different levels in between them. We also have automation stages. If we look at how humans process everything, something gets your attention, you make some sort of inference about what's going on. Is it a fight or flight type situation? Things like that. You make a choice, and then you do some sort of muscular action. Well, we can map this into systematic functions that allow us to break down the different things that we want to do within our network. And you can see here those particular mappings. When we map those together with the levels, we can show how we can actually do things and what type of things can happen and what information we will get back. So if we get all the way up to a 10, we might not get a lot of information back, and sometimes it won't even tell us what's happening because we really don't need to know. So if we put this on a graph, this is what we call the automation continuum, right? Along the bottom, we have the stages, and then we have the automation levels. This is human-driven automation. So in the information acquisition, this is, you might run a script or something to go gather information from devices, run op commands, get some state, maybe look at the configuration or something like that. But the information analysis and the decision and action selection are usually done by humans. Okay? And then you make some sort of action. You can either go out and change something yourself or you run some other script. But in between there, it's consuming automated information as a human and then kicking off some sort of other automation. With an event-driven infrastructure, we can actually raise that information analysis and the decision and action selection on a lot of things that we do. These are things that we do on a daily basis and things that can happen that don't necessarily have to have a human, especially when you gather a lot of data and need to crunch it and figure out what's going on in there. And you know there's only going to be a few options. You can actually codify that. And to get to the vision of a self-driven network, we need to add that machine learning and artificial intelligence type of technology to get up to that level. So the event-driven infrastructure that we're looking at is a stepping stone to that self-driving network. So real quick, we'll talk about control systems theory. And for anybody that's taken a control systems class, I think this was taught in the very first hour of the first day. So a typical open loop control system takes an input signal into a controller. That controller sends a control signal into the system, and then it generates an output signal. In our case, a lot of this is we run some sort of script or a run book. We talk to the devices in the network, and then we get a result. And at each end of this, we have a human being doing something. So what we want to do is we want to think in a closed loop type of scenario. So it starts out with the same open loop, but now what we want to do is we want to take that output signal and feed it back into another system. This can be software. It could be a human if we want it to be, but that kind of takes us back to the human intervention, human-driven automation. So what we do is we take that information through the feedback system, and there's some sort of either error detector or a comparator that makes a decision and generates a new input signal and puts that back into the controller. Robots do this. In robotics, they do this a lot. In oil and gas, they do this a lot from talking to other people in that. So they're constantly putting information back into the system. And sometimes there might be nothing, but that nothing is what you feed back into the controller and say, everything's fine, wait for the next state or something like that. So this is just a graphical representation of an event-driven infrastructure. Things are constantly going, everything's monitored and measured, and as things happen in that closed loop, they continuously take the output, measure it, and push it back in as an input signal. Now, usually when I talk to a lot of customers and network engineers, there's a lot of trepidation about automation, right? Especially taking jobs and things like that. There's no reason to worry about that, really. All we're doing essentially is we're allowing, with automation, the ability to take the things that we have today and make them more complex. And by using automation, we can simplify that. But you have to wrap your brain around how complex things are and how do we automate that. So for those who don't know what shaving the yak is, it's actually out on Wikipedia, but it's essentially everything that goes along with your job. It really has nothing to do with your job, especially in running a network. Okay, it's the creating tickets, it's getting information from the system and putting it all in a centralized place and things like that. So the very first thing that we can do with an event-driven infrastructure is actually stop shaving yaks. Okay. What we do is, instead of, when a lot of people talk about automation, the first thing they jump on is configuration and pushing configuration. It's very easy to do. I've been doing automation for about 20 years on systems and networks, and we've had the ability to do this forever, or since I started. And it's easy to codify and put in, but that tends to be human-driven again. So we want to take a lot of the things that go around that and that are not pushing configuration. They're actually generating tickets and other things like that, and getting rid of that in an automated way. So there is a model to follow to stop doing that, and that's event-driven automation. It allows us to manage the complexity, and luckily with SaltStack, we can manage the scale as well in a predictable and deterministic manner. We know that these things have to happen, and we know how to do them. We just have to make sure that we put that into the system itself to make sure that it gets done in an automated way. We only act when the system's ready. This is where monitoring meets management. This is a Hatchism, as I like to call it, from Tom Hatch. And it really speaks volumes, because now what we're doing is we are not only managing the system, but we're monitoring it, making sure everything's working properly. And if it's not, we can go out and do something. And this is only possible with some sort of reactor decision engine. So event-driven automation in a nutshell, it's very simplistic. The events themselves originate from either devices or applications that we have that run networks. We use filters to sort and apply rules to these events, and then when particular rules are met, we make some sort of registered action occur. So why did we choose SaltStack? Originally, when I heard about Salt, I didn't know very much about it, and I was actually introduced to it by having a discussion with Tom Hatch out of the blue. It was, I think we met at a convention or something like that, but we just talked for about 10 minutes, and he talked about the reactor engine in SaltStack. So that piqued my interest, because I knew that this is something that we have to get to, and we've taken it and used it. So SaltStack is also open. As I mentioned before, it's open source, but also the team themselves are very open to helping us. They've helped us build the modules and let us know how SaltStack works, so that we didn't have to go and learn everything from the beginning. CR has been very helpful with this. It uses known technologies. One thing when we talk about different technologies for managing networks is there's a different underlying system. Things like Puppet and Chef use Ruby. Ansible uses Python. Well, with SaltStack, it's also built on Python, which is essentially the industry standard in networking. It also uses things like YAML and Jinja. So if you're used to those things, learning this, you just need to learn how SaltStack works. You don't have to learn those technologies as well. The proxy structure. Once they came out with the proxy structure, it made managing and interacting with Juno's devices extremely easy. SaltStack is also future forward. They're constantly looking at the next horizon as to how do we take this event-driven infrastructure and make it better, with things like Thorium, where you can use machine learning algorithms to actually do or create events or do things based on multiple events that are all related. And it provides us what I like to refer to as an automation backplane. Instead of you working directly with devices or working directly with applications, now what you can do is you can use SaltStack to actually implement your intent of the things that you want to do, and based on the events that happen, it'll go out and do those things. So anytime that we want to do something operationally to a network, instead of talking to the network itself, now we can use SaltStack to do that. So if there are no questions that are immediate, what I'll do is I'll turn it over to Nathan, and he'll be able to run the demo, and you guys can see what we've built in a typical scenario, a branch scenario where a customer needs to bring up branch devices that come back into a head-end data center and all the work that goes around that. You'll notice in the demo that it doesn't take very long at all. I've had customers that they said that if they needed it done right away, they could usually do this in a day with everything that gets done in this demonstration. But normally it takes, you can measure it on a calendar, how long it would take, possibly weeks to do this one branch. Brett, were there any questions that popped up that we need to answer?
I think we've been addressing most of the questions in the chat, but as a reminder, if you do have questions, please enter them into the chat window and go to meeting, and we'll either respond within the chat window or we'll address it on the audio here. I think, like I said, these questions have been addressed so far, so I think we can just keep going, and we'll check again here at the end of our time.
Cool.
For today's demo, we're going to talk about event-driven infrastructure using SaltStack and Juniper automation. So the demo today, we have a virtualized environment that we're going to show that consists of a fairly typical enterprise/campus network. Some of those things might be opening a ticket, right? A new device comes online, we need to open a ticket so we can track where it's at and all the things as it moves through the process. Some other things you may want to run a compliance test to make sure it has the proper config or the system or a device inventory system, or possibly even configuration management. So using SaltStack and Juniper automation, we can show you how we're going to do that, essentially all automated in a zero-touch fashion. So the whole process is kicked off by a tool we call Jeep, which is the Juniper Enhanced Automated Provisioning System. And then Jeep will handle the initial boot up of a brand new device on the network. So with a little bit of pre-config, you can tell it what OS it should have on it, what config it should have, that sort of thing. So as the device boots up, he'll send out a DHCP request. Jeep will see this. He'll respond back with some extra options so that he can TFTP down a new config, so on and so forth. So while this happens, Jeep is going to be sending out a number of events so that we can capture those events on the event bus and then kick off other tasks automatically in response to those. So this slide just shows a couple of those tasks that we're going to show you today. So the first thing that we'll do is we'll create a help desk ticket in a request tracker 4 system. Then based on that ticket ID, we'll do a number of other things simultaneously. We're going to import it into Juno Space, which is our device management system. Then we'll also run a compliance test using a tool called JSnappy, which is essentially just a tool to make sure it has the right bits of config and the operational state is in the right state. Then we're also going to automatically create a proxy minion inside Salt so that our configuration management system and SaltStack can actually manage that device automatically. And then we'll do a compliance test. When all of those things are completed individually, they'll all update the ticket that was initially created, so we can kind of track this as we go through. So what we will also show is we have a UI called our EDI front end that can kind of help us visualize this entire process, right? So as these devices move through the Jeep ZTP process, they'll be sending out these events onto the event bus, which will get tracked or pulled in by this EDI front end, and then that front end will show you where everything's at. So what makes this all possible is the SaltStack event bus, the proxy minions, and then a number of agents that can sort of tie into that. So this slide just shows that we have some physical network that we can tie in via some proxy minions. We have a virtual network we can also tie in via proxy minions. Then we have actual, physical servers that we can tie in. And then any number of agents can be written to control things like SDN controllers, transport controllers, NMS systems such as Space, and so on. So once we have an event bus like this, it really provides a convenient place to provide a single automation backplane for the entire network. So it's a really, really nice thing to have. So once we have that, we can automate all the things. So with that, let me just go ahead and show you the demo. Okay, for the demo, let me show you a couple of the tools we have. So first, we have everything built in a virtualized environment using a tool called YStar, which is our virtual lab environment management system. Inside here, we have a number of different networks that are all attached together. First of all, we have our corporate head-end network that we call the EDI corporate network, imaginatively enough. Inside here, we have just a fairly typical head-end corporate network. So we have a couple of virtual MXs acting as an edge border router and a gateway router. We also have a virtual SRX acting as our head-end firewall. Then we have a number of servers sitting back here that are doing different things like GitLab, Request Tracker, Salt Master, a couple Salt minions, and then also we have a virtualized Juno Space instance that's going to provide our NMS and device management system. So this is what we'll use to kind of control our branch offices. So let me go ahead and show you what those look like. So we have a number of branch offices built, Pittsburgh, Nashville, Louisville, and Lexington. So if you just pop open Lexington, we can see there that it just consists of a branch firewall and then like a point of sale systems. Keep this fairly simple. So what we want to do is bring this branch virtual SRX under SALT control via this CTP process. So once that happens, as we showed in the previous slide, we're going to open this ticket, we're going to import it into Juno Space, we're going to do a compliance check and a number of other things. So let's just go ahead and get that started, and I can show you what that looks like. So first of all, let's just verify that he's not currently under SALT control. So we can just run saltkey-l, and we'll list all the current minions that we know about. And we can see that we don't have Lexington in there, so that's good. So I'm going to run a script that will simulate the sequence of events that happens from our Jeep system. Because this is a simulated environment, we don't really have a physical SRX to plug in. We'll just run the script to emulate that. So what he's going to do, he's going to kick off a number of events that get fired onto the event bus. And so we can see over here that we have these events being fired off in this Junos or this JSON. But that's not as nice. What we really want to do is be able to visualize that in a nice way. So what we can see here, this is our EDI front end. This is tied into the event bus, and he's going to show us what's going on the network. And here we can see that this device is currently in the configuration stage, and he actually just completed. So that's good. So if we can click on him and get some more details, and this is all things that we just pulled off of the event bus. So I think initially Jeep will reach into the device and pull out things like device facts, like the model, what version of code it's running, that sort of thing. Upgrade the code if necessary. Put all that information on the image bus, on the event bus for us, so we can kind of keep track of where we're at. So, as you can imagine, if you have hundreds or thousands of these things out there, and they're all going through these processes every day, a tool like this becomes pretty handy. So it looks like that device completed. So what should have happened is he should have created a ticket. So we'll log into our ticketing system here, which we use our request tracker for, and we'll just refresh the page. And sure enough, there's our ticket. So we'll just open him, and let's check the ticket history to see what happened. So we can see we had an update that said the Jeep status for Lex Firewall 1 is successful. We had a compliance test that ran against the device via our JSnappy compliance tool, and we can see there that the results are passed. Total number of passed was 1, total number of tests failed was 0. So that's obviously good news. We have another update from Juno Space, device discovery, saying that we did have a discovery job initiated, and there's a job ID that we can use to cross-reference that. And then finally, we had another automation that ran that successfully created a SALT proxy minion. So all good news there. So again, these are things that your typical IT department all have to do by hand as a separate sequence of events. So by using SaltStack and the event bus, we can do all of these things every single time a new device shows up, and they're all just there and ready for further action. So let's go ahead and just check out Juno Space. And sure enough, we can see that he just popped into Juno Space. So now, we can do things like view alarms, we can check port status, that sort of stuff. Normal NMS type things that we can do here. So pretty good stuff. Okay, now let's just hop back on our CLI, and let's go back and look at some of the things that we can do now that this firewall is under the control of SaltStack. So ZTP worked. We know the proxy minion was created. We know that the tickets were updated. So let's just go ahead and see what we've got. So there we go. It's a saltkey-l command. We can list all our minions, and we see that Lex under firewall 1 is there. So let's just go ahead and run some basic salt commands against them to just verify connectivity. So the first thing we'll do is test.ping, and that looks good. So now let's look at the Junos module a little bit. So from the Junos module, we can do lots of things like install configuration, device backups, upgrade software, so on and so forth. So one of the things that I like is the CLI command. So this will just run a normal CLI command just like you would on the device itself, but now we can do it through this Salt system. So we'll just run the show version command. Looks good. So kind of a neat thing that I like to show people is not only can we do this against a single minion or a single Junos device on your Salt control, we can do it against a whole series of them. So I'm going to run the same command against every firewall that we have. That's basically just by specifying star firewall 1 or fire FW1. And so we can see that we can now run those commands simultaneously across all our devices. So this is really like it's Salt kind of the scalability. That's pretty nice. So let's get back and let's check out the config on this guy. So we'll target Lex Firewall 1. And we're going to run the CLI command, show configuration, display set. Just keep it nice and compact. So what we see is a fairly, simplistic config. So our G process essentially just put a config on there that was the absolute minimum necessary to get this thing on the network. We really want all the configurations to be managed via our configuration management system. And so the way that we do that is we can specify lots of these little config snippets that we want to apply to different types of devices or different devices with certain roles. And essentially what we want to do is build up a model of the network. And then this model can be kept entirely, on the file system inside Git or some other backend, like Git or, on the master server. So in our case, we're going to keep these files in Git for this demo. So let me go ahead and show you that. So we'll go over here to GitLab, and we'll just look at our projects. And so I have a project here called Network Model. And inside here, I just have, our SaltStack hierarchy, our state hierarchy, all defined. So this all starts with the top.sls file. So if we just take a look here, this is going to match these various bits of config and these different state files to what devices we want them to run against or to apply against. So the first thing that we have here is a grain match for any device that has the OS family of Junos. And so what that says is for every Junos device on the network, we want to ensure that it has this Junos under syslog state applied to it. Next, we have this minion star, which is a PCRE or regex match. And we want to ensure it has default packages. So that's for every Linux server or just normal server on the network that has a minion name of minion star. In our case, we have minion 1, 2, 3, 4, and so on. And then finally, we have star FW1. And we want to, in fact, ensure that they all have these firewall configs applied. So in this way, we can start to define, roles of devices and then what pieces of config needs to apply to those roles, and then we can push them down. So this is kind of the beginnings of infrastructure as code, but that's probably a topic for a whole other webinar. So we just want to keep this nice and simple for this. So let's go ahead and just take a look at this Junos syslog file, or this Junos syslog model, or state, I should say. So this state file is basically, nice and short. It just says we're going to use the Junos module. We're going to run the install config function, and we want to push down a Junos under syslog.xml template in the templates directory. So let's just take a look at that. And so this is just a normal piece of Junos XML configuration, or at least a snippet. So this just says that for every Junos device on the network, we want to make sure that they have a syslog host that points to 192.168.122.9, and we want to match any event that matches UI commit completed, and we want to send that on port 516. So what this is going to do, we're going to enforce that all our Juniper devices, anytime there's a commit that's done on that box, we want to send that event to our Salt master, where we have a Junos syslog engine running on port 516. So that Junos syslog engine is a piece of code that we have in Salt that will take all of those syslog messages and then convert those onto the event bus. So once we have those messages on the event bus, of course, we can use the reactor system to then run any other state file or any other automation that we want against that. So again, it gets back to that concept of this common automation backplane across the entire network. So now we can plug in everything that happens on our Junos devices, from an event perspective, and then do the same thing. So let's just go ahead and go back to the CLI. And from here, we're going to do a state.apply. And so what this will do is SaltStack will look at that top file. It'll look at this minion, and it'll discover all the things, all the config snippets that we want to apply to this device. And then it'll take each one of those and then push them down to that device individually. So in our case, what we should have is at least a couple. And there we go. So we can see that the Juno syslog was applied because this guy is a Juniper device. And then also because his minion ends at FW1, we also applied our firewall web management config snippet. So let's just look at the config again. And now we should see, if you observe it, you should see a few differences here. Primarily, we want to have set system services web management HT, which is horribly insecure. You definitely shouldn't do it on a firewall. But for example purposes, to keep things nice and simple, we'll just go ahead and do that here. And then we also have our syslog config there. So there you go. So just by setting these files in Git, then we can pull those down to the master server and then push those out to all of our devices. So again, we can target all of our minions and then do this on an ongoing basis. So I think it's pretty common for people to run this out of cron or something like that, just to make sure that all the devices across the entire network are updated, all the time. So lastly, let's just look at the syslog engine. So because we said we want any one of these commits to go to the syslog engine, that's going to go ahead and put that on the event bus. So let's just hop onto this box and, excuse me, and we're going to do a commit, and then we'll watch the event bus, and then we'll see what happens. All right, so let's go edit interfaces, gigi 0, set family INET address. Oh, actually, let's just make something up here. Lucky sevens. 7771.24. Show compare, make sure that that's all good, no other changes are stuck in, and we'll do a commit and quit. And what we should see is those events now start flying across the event bus, and we're going to have lots of things happen from the reactor perspective. So let's just back up here a little bit. And indeed, what we should see, where was it? Here we go. Juniper event Lex Firewall 1 UI commit completed. So this event was put on the event bus. And then what we see is our reactor system found that, and then it launched this Juno's config backup runner that we have configured, which is just a piece of Python code that's going to go out to that minion. It's going to run a show config command that will capture the output of that, and then we'll then again put that in Git and then push it up so that we now have a complete version history of everything that ever happens on that box. So the rest of these events are just some things that happen. So we can see here that we have a Juno's config backup directory of srv get Juno's config backups, and then it'll do a commit and push that up. Here's the minion command where we ran the just show config. So again, that's the runner that did this automatically. And then he's going to pull that down and then push it up to Git, and we see that we have an output of actually a Git commit ID where that was a success. So now we can look at our Juno's configuration backups project, and we can check the repository, and now we can see about a minute ago we had our Lex Firewall 1 config. Our latest commit was there, so if we just take a look at him, and let's look at the config, and more importantly, let's look at the history, and we see we got a couple commits that happened over the last couple minutes. So we can just look at one, and we get a commit time, and also the user, which is root in this case, and then we also see what was changed. So what happens is we have this complete history now that's automatically snapshotted for us every time something happens. So I think that's it for the demo. I'll turn it back over to Eddie, and I think we'll take some questions.
Okay. I know we ran over a little bit on time there. Thanks, Nathan, for doing that and getting it in there. So, were there any questions? I was watching the demo.
Yeah, I think we've addressed most of the questions within the chat, and they seem to be satisfactorily answered there. We just did have one come in. Maybe we'll take this one and then do it considering the time. We should probably wrap up. So the question is, for a large number of devices, is there a way to run a lighter Junos proxy? 400 meg per device on 1,000 devices, equaling 40 gig.
Yeah, actually, we've only done a limited amount of testing. as far as scale goes, and I was actually surprised to see that 40 meg size when CR said it, because we haven't seen anything get quite that large yet. So I don't know if it's because our modules are smaller. I'm not quite sure, but we haven't seen that. But that's a probably good number to hit, right? 40 meg, because it won't go much bigger than that. So.
And in fact, you don't have to run all of those proxy minions on the same machine. They can run on a number of different control nodes. So you could spread those out to several servers if you needed to.
Right. And we've actually done that. We've used multiple VMs to run different minions on. We didn't do any scale testing, but we did that to make sure that it would work. So.
Okay. And then it looks like Nitin is chiming in the chat as well on that question. So, okay, again, we've gone over time. We apologize for the late start and the technical difficulties there, but Nathan and Edward, of course, CR, thank you for your time today on this webinar. We are recording this webinar. We'll make it available to all attendees here, most likely within the day. So watch your email for that. And thank everybody for your participation, and we'll be in touch.
Thanks, Red. Thanks, CR.
Thanks, everybody.